Connecting Claude to your proprietary enterprise data requires a system for Retrieval-Augmented Generation, or RAG. The baseline approach involves converting raw documents into vector embeddings and storing them in a single, centralized vector database. In this standard configuration, a user query triggers a similarity search against the database, which feeds raw text chunks into the Anthropic API. But in complex environments, this simple flow often outputs an error or a low-quality response. In large-scale production, a standard vector search often retrieves irrelevant text or fails to locate the target document entirely, leading directly to model hallucinations. This occurs because a single similarity search cannot technically distinguish between structurally different documents, like a granular technical manual versus a general policy, when they share broad semantic themes. Building reliable machine learning applications requires a deterministic, multi-stage retrieval pipeline to replace the simple database connection. Scaling enterprise AI effectively requires rigorous structural pipeline engineering. The performance of the prompt depends entirely on the precision of the underlying data delivery. Before a user prompt reaches AWS Bedrock or Google Cloud's Vertex AI, it must be matched against the correct segments of your data infrastructure. While an enterprise may manage terabytes of information, the context window of a large language model is strictly limited. Only a minute fraction of your total data can be sent for processing at any given time. Sending massive context payloads to the API creates a mathematical trade-off. Increased context size results in higher latency and significantly higher token consumption costs. Claude's intelligence and reasoning are effectively constrained by the quality of the specific data payload it receives. The model cannot reason about information that has been omitted from the context. The core engineering objective is to identify and retrieve the exact, highly relevant data chunks from millions of possibilities in a matter of milliseconds. Mastering this context retrieval phase determines both the technical viability and the unit economics of the entire system before the model generates a single token. Data ingestion begins by breaking raw documents into discrete text chunks. Engineers must determine the optimal chunk size to preserve enough local context for the model to understand the text without wasting tokens on irrelevant surrounding data. These chunks are processed by embedding models into multidimensional coordinate arrays known as dense vectors. This allows the system to search for semantic intent. The database retrieves chunks mathematically similar in meaning, rather than just matching characters. However, dense vectors frequently fail to retrieve exact keyword matches. Specific serial numbers, unique names, or proprietary internal acronyms are often missed because they lack broad semantic relationships in the vector space. In enterprise systems where exact precision is required for technical or legal data, relying solely on semantic similarity is a significant architectural liability. Solving the exact match failure requires a dual retrieval architecture that adds a keyword matching layer alongside the vector search. This layer uses sparse BM25 search. BM25 scores documents based on exact keyword occurrence. By executing the query through both paths simultaneously, the system captures both semantic intent and alphanumeric precision. This configuration, known as hybrid search, runs the dense semantic path and the sparse keyword path in parallel. The outputs from both retrieval methods are merged into a single, unified pool of candidate data chunks. This approach maximizes system recall, ensuring the target data is present in the results regardless of how the user phrased their request. At enterprise scale, running a hybrid search across a monolithic database containing millions of documents severely increases system latency. Searching through vast amounts of irrelevant data wastes compute resources and directly delays the Claude API response. To maintain speed, the architecture uses specialized index silos. During ingestion, data is segmented by domain, separating codebase, HR policies, and server logs into high-performance indexes. A query router node classifies the user's intent, directing the query only to the relevant silo, ignoring the rest. Pre-search routing is essential for preserving millisecond latency and API efficiency as the document count grows into the millions. Hybrid search over specialized silos provides high recall, but it often returns more candidate chunks than the LLM should process. Feeding an oversized candidate pool into Claude introduces noise, increases token costs, and can interfere with the model's reasoning process. The pipeline requires a precision filtering stage called re-ranking to condense the results. A dedicated cross-encoder re-ranker model evaluates every retrieved chunk directly against the original user prompt. The re-ranker assigns a precise relevance score, overriding original search rankings and discarding the least relevant information. Re-ranking shifts the system from broad recall to high precision, ensuring an optimized signal-to-noise ratio for the language model. In the final assembly stage, the top-ranked chunks are carefully formatted into a structured JSON payload alongside the user's prompt. This complete architectural sequence ensures context quality by combining routing, hybrid search, and re-ranking. This refined payload is then transmitted to Claude via the Anthropic SDK on Vertex AI or Bedrock. By ensuring the model receives only high-value verified data, this rigorous multi-stage approach effectively eliminates hallucinations in production. Contextual retrieval functions as a deterministic engineering pipeline, allowing developers to balance intelligence, execution speed, and API costs in production environments.